Let's look at total internal reflection, problem 5. And in this case, we have a density column. We have water, N is equal to 1.33. And above that, we have ethyl glycol, which is N is equal to 1.36. And then air above that, N is equal to 1. And what we're going to do is figure out what angle with respect to the normal with a light in the glycol. This is, I'll just put the name here, glycol. And this is water here. This is air. What is the angle with respect to the normal so that will the light in the glycol that's hitting this interface with the water no longer refract into the water? In other words, when will it achieve total internal reflection? So what's the critical angle? That's what it's asking. See if it makes sense. First of all, we're going to a higher index to a lower index. Though ever so slightly, that is the condition necessary to have TIR. So let me do a normal. And so basically we're going to refract to 90 degrees. Okay, as the incident angle, as the incident ray here is at the right angle. So we got the critical angle here as the incident. That's equal to the incident angle. And so that's really all it's asking initially. And then we have another question to answer as well, which is how do we shine it from the air into the glycol? But in the first case, let's just go ahead and it's just a simple and direct application of the critical angle situation, which is that sine of theta critical is N2 over N1. Okay, which is N2 in this case. This is the second medium, so it's 1.33 over N1, 1.36. And that's equal to 0.33 divided by 1.36, which is 0.978. Maybe I'll just use that fraction in the analysis here, namely theta critical is equal to the inverse sine of, well, the 0.978, which is second sine of -1, second answer equals 77.9 degrees. And so that was our answer. That's this critical angle. Now, in the next case, how do we shine the flashlight into the glycol in the first place to achieve this angle, which is the, this angle here is the refracted angle is the same as the incident angle over here because of alternate interior angles. So this is 77.9 refracted. And so, let's see. This is a higher index, so it goes toward, we got to have a lesser of an angle here, if anything, right? Well, greater angle with respect to the normal for the incident, so that the refracted is bent toward the normal. But it's 77.9 degrees, so that's already, I don't have this drawn correctly, that's really, it should be drawn more like this. So we can't get a whole lot bigger than 77.9. So let's see how that works out. Kind of like part B to this thing. So basically, we're going from air, A-I-R, to glycol. That's the deal. So let's use the N1. Sine of theta 1 is equal to N2, sine of theta 2. So we're really looking for this angle here. That's what we want. So I'll write it as follows. Sine of, and this is, N1 is just 1. So sine of, let me just write it out, just make sure. Sine of theta 1 is N2 over N1, sine of theta 2. But we know what sine of theta 2 is. It's sine of 77.9. So anyway, this is equal to N2 is the 1.36, N1 is 1. Sine of theta 2, 77.9. And that is equal to approximately 1.33. That's the sine of theta 1 is 1.33. The sine of this angle. Okay. Inverse sine of 1.33 is equal to, you know what that calculator gives you when you do that? Second inverse sine of, big question mark. In fact, there is no solution. No solution. So this situation we have here, this hypothetical situation, can't be achieved. Yes, we could take the light and put it at a 78-degree angle here, but there's no way to position the light. You know, no matter how close we get to the, no matter how glancing it is, when it refracts into the glycol, it's going to bend insufficiently to produce the total internal reflection. So, can't be done. That's the answer.